Hi, once again, my name is Spencer. I'm a fourth-year medical student here at Columbia. In this video, we're going to talk about two really important built-in functions within R, the if function and the for function. I'm also going to import the tidyverse library for later, but don't worry about that right now. Often when you're processing and analyzing data, you'll want to check if some condition is met. This relies on understanding logical variables, which are covered in a previous video, and the if command, which we'll go over now. The if and else commands are very straightforward. They just check to see if the input is true. If it's true, you can tell it to do something. If it's false, you can tell it to do something else. So here's an example. I define my variable x as 5. Then I say, if, parentheses, x is greater than 4, these are my conditions I'm testing. If that is true, print 5 is indeed greater than 4. I have to place anything I want it to do inside these curly brackets. And then I say else. So this is if it's not true, then I tell it to do something else. In this case, it would print the laws of mathematics have changed and humanity is doomed. If I run this command, you'll see that 5 is indeed greater than 4. So this command, x greater than 4, was in fact true. Now, any function that returns a logical value can be put into an if statement. This includes is.na, is.numeric, and so much more. You can even put variables that contain logical values as the condition. So here, I define my logical as false. Then I do an if-else command loop where I say if my logical. If it's true, it'll say my variable was true. If it was false, it'll say my variable was false. Because I defined it as false, I know that if I run this, it'll say my variable was false. There are other common operators you might also use. There's greater than or greater or equal to, less than or less than or equal to. There's equals, which is a double equal sign, as I've talked about in previous videos. And there's not equal to, which uses an exclamation point next to an equals. So here I'm just going to show a couple examples. So when I do the command if y is greater than 4, we know this should return false. So if it were true, it would produce this command. If y is less than 4, which we know is true, it should produce this command. If y is equal to 4, which we know is false, it would produce this command. Finally, if y is not equal to 4, which we know is true, it'll say this command. If I run all of these, you'll see that the only ones that actually print out are the ones that were in fact true. So 3 is indeed less than 4, and 3 is indeed not equal to 4. Sometimes you'll also want to combine multiple conditions using the following commands. These two vertical bars, which are available on your keyboard above the slash command, signifies an or statement. This means it will turn true if at least one of the conditions you specify is met. The double and symbol signifies an and statement. This returns true only if every condition is met. So we're going to test this out by using a variable that we store as x. Here I'm going to define x as 5. Here are some examples of or statements with just two conditions, but you can do as many conditions as you want. Here I test is x greater than 1 or x is greater than 1. Obviously these are the same command, and so both of these are going to return true because x is equal to 5. If I run that command, it'll say yes, at least one of these statements is true, but maybe both of them are true. Here I show an example where I test is x greater than 1, which we know is true, and is x equal to 1, which we know is not true. Well, because at least one of them is true, we know that we will print this statement. If I run these commands, you can see that that is in fact the case. Here are some examples of and statements with just two conditions, but again, you can do as many as you want. Using the same x value, which we set equal to 5, I'll test is x greater than 1, and I'll test the same command again. Here, both statements are true, so it will print this statement. But if I run a different command similar to we did before, I test if x is greater than 1, which is true, and I test to see if x is equal to 1, which is not true, I will get a true and false. When R sees this, it'll say if true, you print this statement. If false, you print this statement. When I run it, you can see that in the first comparison, both statements were true, so it printed out my command. And in the second one, because x equals 1 returned a false, it says at least one of these statements is false. Doesn't mean both. Doesn't mean that any of your conditions are causing errors. It just means that only one of them is in fact true, while there's some sort of falseness going on elsewhere. You can also nest if statements inside each other. So continuing with our example, we have x is equal to 5. First, I can test if x is greater than or equal to 1. Here we can see that it's true, and so it would move inside this command to test for something else. So then I can test a new command. Is x less than or equal to 6? Well, we know this is going to be true, so this would then print out this statement, x is between 1 and 6, inclusive. I say inclusive because I used greater than or less than equal to. If it were greater or equal to 1, but not less than or equal to 6, then it would have said x is greater than or equal to 1, but not less than or equal to 6. If it had been less than 1 in the first place and never got to this part of the code, it would have skipped straight to the else and said x is not greater or equal to 1. We didn't even get to evaluate if it was less than or equal to 6. But of course, we know that it would have to be consistent with the rules of math in that situation. So if I run this, you can see that x is indeed between 1 and 6 inclusively because x is equal to 5. A practical application of this might be to create a new variable in a dataset based on conditions of other variables. So let's import our county health rankings and try to do that. Here you can see I've properly loaded in the data. We can see that the first row when we get to a state doesn't refer to a county. It refers to the state overall. Perhaps we want to check if the row is indeed a county or state. In this example, you can see the first row of the dataset was Alabama, but it referred to a lot more deaths, a lot higher numbers than everything else, because this refers to the state overall. So if I check for this first county, just getting the first value, and I check the type, you can see that this so-called missing value is actually a character, which is why we need to be careful about what missing data is encoded as in R. So with this missing data encoded as an empty character, this means that every observation referring to a state overall would have to have an observation of the county variable equal to this empty character. So let's construct our if statement with this in mind. It's going to check if the overall DF going to the variable county, just the first observation, so this means the first row of the county variable within my overall data frame, check to see if that value is equal to an empty string. If that's the case, we know that the row is a state. If that's not the case, it actually has a name for the county. That means that the row is a county. If I run this command, you can see the first row is in fact a state. Now let's try it out on our 2,470th row, which I randomly selected. This is Zeeback County in South Dakota. This county is one of the poorest in the United States, with a child poverty rate over 60%, which is higher than any other county in the country. Unfortunately, this poverty is affecting a community that is over 70% Native American. They don't have access to many of the resources that people in larger cities often have. Here you can see that I've pulled out this row and has some missingness in some variables and lots of other variables with information. So let's confirm that this actually refers to a county using our if statement. Again, I'm going to look at the county variable inside the overall DF. I'm going to look just at the 2,470th row. I'm going to check if it's equal to an empty string. If it is empty, it'll say it's a state. If it's not empty, it has an actual name, it'll say it's a county. When I run this, you can see that that row is in fact a county. So child poverty is bad, but at least we have the data to identify it so we can do something about it. That's where we come in as data scientists for health equity. But focusing on the coding aspects, it's cool that we can check if statements for a single value. But what if you want to do the same check over and over for the whole data set? If it seems like you'd be doing something that's very repetitive, you may need to try out a for loop. There are other ways to do this that are more efficient, but it's beyond the scope of this video. So a for loop allows you to iterate repeatedly over an action so as to save code and time. The format is as follows. You say for, parentheses, and then whatever counting variable you have, the word in, and then you specify some vector. So here's an example. I define a vector as my animals. I then establish a for loop. I say for, and then I get to name whatever I want. Each animal is how I'll refer to it. And I tell R that I want you to look in my vector of animals, my animals. Everything inside these brackets is what they will do for each of these animals. In this case, I just want it to print the value that it's seeing. So when I run this, it will just go through each part of this vector and print out the animal. You can also specify numbers as your counter. The following command does the same thing as above, but instead it navigates using the indices of the vector. So here I say, let's call my counter variable I, and I want to go in 1 to the length of my vector. So the length of my vector was 5. So it says go using the variable I in a vector from 1 to 5. So in order to have it print out the animals, I need to specify my animals vector and print out the ith observation in that vector. You'll see that that prints out the same results. Now let's put this to practical use in our county health rankings dataset. Earlier, we were able to create a command to check if a row contained a county or state. So I've just repeated this above and showed you that when I set I equal to 1, which was Alabama state, this was in fact a state. Now, let's try doing this for the first 200 rows. Copying and pasting the code over and over would be a nightmare. So instead, I'm going to run a for loop. I say for I in 1 to 200, so all the numbers from 1 to 200, check the name of the county and compare it to this empty string. If it's an empty string, tell me it's a state. If it's not an empty string, tell me it's a county. I also use some complicated paste commands that you'll learn about when you manipulate characters in another video, but this just helps me for visualization in this video. When I run this command, you can see that row number 1 is a state, as we saw earlier, and then there are a lot of counties, and then row 69 was a different state, row 99 was a state, row 115 was a state, and so on. So now, what if we created a variable for identifying if the row is a county or state for all observations? We're not going to print it out like we just did. We'll actually store that information. So for now, I'm going to define a new variable that will say either county or state. So I have my overall data frame, I use my $, and I use county or state as the name of my new column, and I set that equal to just missing values for now because I don't have information. Then I say, okay, I want you to do a for loop where you go using the counter I from 1 to however many rows there are in my overall data frame. So this will go from 1 to over 3,000. And it's going to do the same check that we did before. However, if the county name is equal to this empty string, which we know means a state, instead of printing out something, I'm going to store the word state into this new variable that I've created. You have to specify I here. If you don't, it's going to define that for the entire vector, the entire column, but you only want it to specify it for the specific observation in your for loop. Similarly, if it is not an empty string for the county, then we know it's a county and it does the same idea. If I run this, it won't display anything, but we actually know that it did in fact run. So now we can check out our new variable using the table command. When I run this, we can see there are 3,140 counties and 51 states. I don't know about you, the last time I checked, we only have 50 states in the United States. So what is the 51st state being counted? Maybe we should create a new data frame where we only have observations that are labeled as states. This combines your knowledge of if statements and your understanding of how data frames are navigated. This next command will do the following things. It names a new data frame, states only DF. Then it says, look inside the overall data frame. And then it defines a condition. It says, look to see if this new variable we've created, the county or state variable that we had just examined, if that equals to state, keep only those rows. Earlier in videos, we talked about how everything before the comma refers to a row. So this will say, only keep observations that are equal to states. If they're not, it'll be excluded from our new data frame, the states only data frame. So I run this command, it doesn't view anything. And now we want to actually look at this states only data frame and see what the culprit was. When I run this, you can see as I scroll down that the District of Columbia, as you might have guessed, was being defined as a state because there was no county below it. That's probably fine for our data set, but it's something to be aware of. We can also do a similar idea for counties only. In fact, you've seen something like this throughout almost all of my videos. Here I define a counties only data frame. I say, okay, go into our overall data frame that we imported from our data file. And then we're going to define a condition. We're going to say only keep the ones in which the county or state variable that we just created are equal to county. I define that before the comma to specify the rows, and then I can run it and see that I've only kept counties and I've excluded the first row, which would have been a state only. In actual data science practice, many people like to use tidyverse commands to subset their data frames. We can achieve the same states only data frame using tidyverse commands that might be a little easier to read. So here, I'm going to find a new data frame, just calling it my second try. Use the assignment operator and say, okay, using the overall data frame, using a piping operator telling R that we're working in tidyverse, I want to do a filter. This filter command will then say, okay, check for this column in our data set and keep it if it's equal to state. So when I run these commands, you'll see that this new data frame, states only df second try, produces the same thing we saw only with our states only data frame. Hopefully this video gets you a little more comfortable working with if and for statements. They're really pivotal parts of the R language, and so you'll get more used to it as you practice. So now you try. Import the overall county health rankings dataset and limit it to the counties using these commands. As you notice here, I actually use a very similar command to what we just talked about in this video. This allows us to subset to counties only. Then you're going to define a new variable that divides the counties into either small or large counties with populations of a cutoff of 100,000. How many of each size of small or large counties are there? Can you create a new data frame that has only large counties? To make this easier, we've provided skeleton code for you to be able to code this out much more simply. So using this code, replace your own code in all of the indicated places to try to generate a new data frame that describes the different sizes of counties.